Hi guys, good morning. Firstly, a really big apology that yesterday the video could not come because I just landed back in Bangalore and like my health got worst as soon as I reached back home. I could not even properly sleep. I don't know what was happening, like my stomach ache, vomiting, all that stuff, all this gross stuff, it happened. But yeah, here we are with the next type of problem, which is the next type of BFS problem which you can encounter. So basically in the last video we saw, okay, a standard BFS, you have a node, you have a neighbor, you have to do a shortest path. So you just go on to the neighbors like this and you're good to go. Now, the next kind of BFS which you will encounter, see, firstly, when I say I intro the video, it's actually a lecture rather than a problem video. So it's the reason I told you pre-head, okay, it's a problem of BFS. But as soon as I start the problem, please forget that it's a BFS problem and I will just show you the intuition, how to actually reach to the specific that, okay, it's a problem of a BFS. So yeah, here we'll see the BFS on a matrix. I swear it's super important, super important. I have given many interviews in this, like specifically a problem of a matrix in which just you have to do a BFS. Basically, they just do a easy and a hard in the same problem of a BFS. So I swear it is more important than the standard BFS of the nodes. You go on to the neighbors, like standard graph or a tree BFS. It's more important than that for an interview perspective. So yeah, let's see. Basically, I initially grabbed this particular problem, rotting oranges, but then I realized, okay, it is the better problem, which is the shortest path in a binary matrix because it is much more complex. And you will see how. Firstly, let's understand the problem pretty easily. It is just an n cross n binary matrix called as grid. We have to return the length of the shortest clear path. Mark my words, shortest clear path. Firstly, when we hear shortest, okay, our ears should just wake up. BFS, DP, simple, array, anything could work. But okay, all these are possible options. But we have not read the problem completely. Let's see how. In matrix, if there is no clear path, we have to return a -1. And a clear path, what this clear path is not a standard term, right? So what is a clear path? Clear path is in a binary matrix is a path from the top left, which means the 0,0 to the bottom right, which means n-1, n-1. If there are n rows and n columns, so from 0,0 to n-1, n-1, it's a path. It's called a clear path. All visited cells of the path should be 0, which means I can only visit the cells which are marked as 0, and also all the adjacent cells of the path are directionally connected. See, in the problem you will be always be given in a matrix, if you are just about to move to a next cell, you will be given, okay, can you move to the 4 cells, which means if it is given the 4 directionally connected, then you can move from here to top, left, bottom and right. If it is saying it is 8 directionally connected, then you can move in all the 8 directions, which means diagonally also you can move. So please make sure that you read this condition carefully, okay, how you can actually move. It is the reason that I took a 8 directionally connected problem rather than a 4 directionally connected problem. Now let's see. It's just saying, okay, the length of the clear path is the number of visited cells of this path. Okay, cool. So we just have to find out, okay, the shortest clear path, and clear path is nothing but the cells which are visited. If I just go on from here, then I just know, okay, I can't go down, cool, for sure. I'll go here, then I can go here, I can also go here, right? Then from here I can just go here or I can go here. So as you can see, the shortest clear path is, one option is that, okay, I can't go here, so one option is I go from here to here, then okay, again I can go from this cell, I can go here or here. The path right now will be 3, here it is 3 and here it is 3, cool. Then from here, one option is like now I'm standing here, and one option now I'm standing here. At one step I can go to the next cell, which means now the length of the path will be 4. Next option will be, now my length of the path will be 4. As you can see, I reached my final cell earlier because of the path right here. So it is my shortest path. Now, okay, you understood the example pretty clearly, but you saw what happened. I started from my main starting cell and I tried to spread down. I tried to spread and I tried to reach the final cell. Okay, I started from the root node, which means the node which is 0, 0, and I tried to spread. So I could just go to every possible location and try to find, okay, can I reach there? Can I reach there? How early I can reach there? As you can see also here also, I tried to spread here also, and then again I was going from here also. I was trying, okay, if I can reach from here also, I was trying, I can reach or not, and from here also I was trying, I can reach or not. It's the reason I am at starting a position. I'm just trying to spread to the positions nearby so as to reach to my final location as early as possible. As early, which means shortest. Spreading, which means breadth. So it's the reason we can think of using breadth first search in this. Breadth, spreading, shortest, breadth first search. Cool. Let's see the example pretty quickly how it is the spreading is being done. I specifically made this example. It is the most comprehensive example you can find to actually understand, okay, how this spreading is actually effective and it is needed. So basically I have to start from this particular cell right here. Okay, if I start off, I have to spread out, right? Because I need to reach to my, basically it's like that. Okay, I have a poison here and I need to make that poison reach the last cell as soon as possible. So it will just try to spread, go, spread, go, and reach that final location, which is this kind of a maze thing. Now it starts from this cell. Okay, it reached to the neighboring cells. As I said, it's four directionally connected, so it can reach every of those cells. But you can see the one right here is not a valid cell, and outside boundary is also not a valid cell. So the only location it can move is right and bottom. Cool. It just moved. It is now here. Again, it will just try to spread individually. It will just go and spread. I'm only moving at the possible locations. It will just go and spread. Again, it is here. It will just go and spread. It's here. It can just go here and here. It will just go here and here. Now it is here. Cool. It landed here. Now it landed here. At this point, it can go up also and bottom also. Right. Back it cannot go because it is not visited yet. But as soon as it goes here or here, as you can see here, it reached and it has reached the final position. So you can easily see I'm just spreading from my initial location and trying to reach to my final location as soon as possible. Because as I'm spreading, so basically I'm from this cell, I spread, I just mark it as visited. So I don't have to visit that again, which means, okay, if I've reached to a cell, if I've reached to a cell here, it means I've reached it first time and as early as possible because I was spreading at every unit of time. Now, it's a thing for the people who have studied DP and the same kind of problem in DP. A few people might just look at this problem and will say, okay, I have seen this problem in DP grid problems. Aryan, I will solve it via DP. Because it's more intuitional. I have learned DP before and I can solve it via DP. Because it's the same kind of problem in DP also. So is it that it can be solved by DP? Because it can be solved by a BFS, but a few people have an issue, okay, it can be solved by DP because it's an not exact, but the same kind of problem in DP also. Minimum cost path, a DP problem. But the twist here is that you can only traverse down, right, and diagonally lower, which means lower cell. Which means at any point of time you are just moving right or down. You are never moving up. Which means that if you apply DP, because in DP what do? You just apply a for loop which just goes row wise, which means it just goes down only. But in a problem, it was just saying that I can go in every direction possible, which means I can go directionally, which I can go up, diagonally up, left, up, anywhere I can go. So it's the reason why it will fail is if I just apply my DP on this problem, then it will just try to go right and down, right? It can't go, it can only go down. It just reached end, but it has not reached my final cell. So visited for this cell is 0. It has not been visited. It can only reach here. At max, it can reach here. It can't go here because, okay, for sure. So it can only reach up till here at this point. At this point, it can only reach. It is not visited. It will just return a -1. It will just say I cannot reach at all. But I can actually reach. How? I can just go down, right, up, right, down. I can finally reach. Answer will be 16. It's the reason. As we can go all directions. I can go all directions. I can go up, bottom, down. Thus, I can visit that cell as I want and as early as I want and only one time. It's the reason I have to apply a BFS rather than a one directionally DP. It's the reason we have to use a BFS rather than a DP. Okay, now you know, okay, Aryan, I will just move from one cell to the all neighboring cells because the neighboring cells are my neighbors and I'll just try to go onto all these cells. But what are your neighbors? You know, your neighbors are the cells which are directionally connected. But for a cell, you only know the I and J. For the neighboring cell, you also need to know their I and J. If you know this I and J for the cell right now you're standing at, so you also have to know to actually move to those neighboring cells, you actually have to know, okay, what are those neighboring cells coordinates? So it's nothing but I comma j plus 1, I plus 1, comma j plus 1, I plus 1, comma j, as we just do. +1 for going row 1 down, -1 to go row 1 up, +1 in j to actually go my column right, and -1 in column to actually go left. It is, we can apply the same thing to actually go on to the next coordinates. How we represent in the code? It's that we can take a directionally a direction 2D array, or we can also have a 2 1D arrays, which is, let's say, direction of x and direction of y, rather than having this 2D array. But if it is more convenient to you, like you can have this, or you can have two direction x and direction y 1D arrays, which will just say, okay, 0 0 1 1 and so on, like, and it will have, let's say, 1 -1. It will just, okay, a pair of this can actually go one time. So I can just have a 0 comma 1. It will just say me, okay, from I comma j I can go to I plus 0 j, I plus 0 j plus 1. It means that, okay, if I have this coordinates, I will add this particular direction to actually reach to my neighbors, which means I plus 0 comma j plus 1. What is this? It is nothing but the right cell. And similarly, I can go on to every of those 8 cells, neighboring cells. Pretty good. Which means to obtain this next coordinate, which means the next x and y, which means the neighbors x and y coordinates, I just grab the current coordinate, which means I and j. It is I and j. It is the next sign, next j, and direction will actually move on to every of those 8 directions and see, okay, what increment I need to do in I, what increment I need to do in j. And with this, I can get my next x and next y, which is the next coordinates of my neighboring cells. Okay, I just figured out I need to do a BFS. I just figured out how I will iterate. I will go on in my BFS, which means I can go from a node to actually its neighbors. I just know that. What else is remaining? Nothing, right? In a BFS, you just need to know, okay, you have to apply a BFS, and second, how you will apply, which means, okay, from one cell, how you will go on to its neighbors. And it's standard that we will visit a node exactly once. So it's also very standard use case. We have a queue to actually push in our node, and node is represented by a coordinate of my cell, right? Because I just said that the same thing. I have this I and j. It is my node. Its neighbors are nothing but I comma j plus 1, I plus 1 comma j minus 1. It's nothing but the coordinates which will help me. Okay, it is a node, it is a neighbor. So I can have that in our pair or a vector in our queue. Cool. Thus, it is what we have to do ultimately. I highly recommend to code by yourself. It's pretty easy, but still, I'll show you the code, because in the code, there is a very fun, tricky part, which can actually, see, you can actually code it by multiple ways, but I'll show you the easy and the most intuitive way to actually code this. But yeah, let's see. I don't know why it's lagging, but yeah. Firstly, very standard base. Firstly, I just have my m and n. No worries, pretty cool. Then I have my base case. Okay, if if my base cell, which means my starting cell, is already a 1, I cannot reach, or if my end cell is already a 1, I cannot reach, because I can only travel on the cells which are 0. So it is pretty good, pretty cool, done. Now I have the same direction 2D array as I showed you above. I have this visited thing. Now it is to actually see, okay, what all cells are visited, so that I only visit a cell once. I'll also show, okay, you can actually optimize the same thing by not using this visited cell, and also just modifying that particular grid to actually, like, let's say -1. If I can just say and check, okay, if my grid is -1, it is already visited, so I can modify my grid itself. But in production codes, it's not recommended to modify the grid. So in interviewer, if you are just saying to the interviewer that, okay, I can modify the grid, just make sure you also add a point that, okay, in production codes, it's not recommended to modify the grid, but for an example, it is how we can optimize it. That's it. Cool, no worries. Then I'll just go on and visit my first cell as true, because now I'm starting from the cell, so it's true. Standard BFS, I just have this Q. Q is actually of a vector, or you can also have a pair. This vector will store I and j coordinates. You can also have a pair because it's just the 2 coordinates which I need to have. Now I just push that in my Q, which means the first coordinate I have. I will have my answer as 0, which means I'm starting from the cell 0. So I'm starting from the first cell. Ultimately, see, what's happening is, if I'm starting from here, let's see this example back. If I'm starting from here, if I go, initially here it is 0, then it will be 1, 2, 3, but the answer is 4. So ultimately, I just, whatsoever answer I get, I just need to add a +1, because I'm starting from 0. Or I can ultimately start from 1 also, so then I can just have 1, 2, 3, 4. I can return a 4 also. I am starting from 0, so I'll just add a 1 in the last. Cool, no worries. You can see that the same thing also, I'll return a +1 in the last. Cool. Then I'll just simply do BFS while not Q is empty. Then you can just see one thing. There's a slight modification in the Q. I just grab the size and I am just iterating on the current size of the Q as soon as I enter my Q. Why? It's because if right now I have this many elements in my Q, then as soon as every element is done, which means, okay, I just grab this element, I'll just add my neighbor in the queue. So I need to, in one shot, I need to evaluate all these elements which are already initially in the queue, and later on, whatsoever neighbors they get, let's say these are the neighbors they can get. So like next iteration, I will evaluate all these neighbors in one shot. Why in one shot? Because for all of these, my answer will increase by 1. For all of these, my answer will increase by 1, because all these are simultaneously going on to the next neighbors. It's the reason for my particular elements in the queue right now, which means for this particular group of queue, after adding the neighbors, it will just keep on increasing. But right now it is the queue right now. So after evaluating all this, my answer will increase by 1, because after all these elements of queue right now I can go to the next element. It is the reason. It's the reason I took this question, because here you can easily see, okay, the queue, the BFS can also be modified if I want to evaluate my particular group of nodes together. Or the other option is that you can have another attributes as a distance, and you can just grab that distance in your vector itself, and you can just go on. And like after, if you grab that distance thing, then you can have a simple queue and you don't need to have this. It's the reason I specifically choose to show you, okay, how you can actually evaluate only those queue elements, because in a queue, at every step, your element will get added. So if you don't have the condition where you have to stop, you will just go on evaluating the neighbors also. But at this point, I just want to evaluate my only these particular nodes which can actually go to the next neighbors. I go and evaluate these particular neighbors, which means these particular elements, and I just see, okay, if I have reached my final cell, I can just return the answer +1. I showed via +1. Then I just go on to all of these 8 neighbors. I just grab their ing coordinates. I just check, okay, if it's a valid coordinate to go on. How to check the valid how to check if the coordinate is valid? If it is not visited already, if it is a 0, and if it is in the bounds of my matrix, then it is a valid. If it is valid, then I'll just push it in my queue, which means pushed in my queue, and also mark it as visited because ultimately it's visited. For all these elements right now, my answer will increase by 1 because ultimately, see what happened is I will push like the particular element. Let's say it is 1 comma 2, sorry, 0 comma 1 and 1 comma 0. So it is 0 comma 1, 1 comma 0 in queue. Now when it will go out of queue, then it will actually push in the next element, which means 1 comma 3 in queue. But actually I just want, okay, at one step I need to only evaluate only these two elements and not the entire queue itself, because it will just remove, add, but I need to make sure in the start itself I need to only evaluate these two elements, which is the actual size of my queue. Thus I just put that condition inside my queue, which is the size. Ultimately I just return -1 if it cannot visit my cell, which is m-1 comma n-1. I hope that you guys understood it. Time complexity is nothing but simple of n square, because you have, in worst case, you have to go at every cell of this particular matrix. Space is also of n square because you are using a visited array, and if not even visited array, then you also can have to use a queue. In worst case, it can go up to O of n square, and exactly not O of n square, because if you just use it, then at particular time it will have 8 elements, then you will just go remove those 8 elements and just add another elements. So it's primarily because of visited array, but you can't avoid to actually not use it because it's not a good practice to actually remove those elements. If the interview wants, you can just like let him know, but still it's just recommended that you just not use it. So like just state this condition and he would be good to hear this from you. Now modifications, I told that, okay, you can have a queue of pair comma pair because you're just having 2 elements. A pair is much faster than a vector, mark my words. So if in future you are like giving any competitive programming contest and your vector of something, like you have, let's say a set of vector or a queue of vector, and if it is failing and you only want 2 elements or 3 elements, just try a pair of pair or a pair. It will just work because a pair is much faster than a vector. And ultimately the codes of C++ and Java are both down below for you guys to understand it. I hope it's exactly the same. I hope that you guys understood the explanation why BFS was required. How we, okay, when we know, okay, we can do this via a BFS, then we choose, okay, what we need to push in my queue, how will I visit it, what neighbors I have to go to, how will I identify, okay, it is a node right now I'm standing at, and what the neighbors I have to go to, and if it is required to actually go on to my neighbors only specifically, okay, next step I have to go to my neighbors and all that stuff. I hope that you guys understood it. If yes, then do the like button and you can solve all these problems, both of them. And also I have compiled the whole list of problems in our list, which is given below in the description. It is having the problem of BFS, and we will keep on updating for this, for DFS, the extra, MST, any problem which you will encounter in future. So yeah, it's all from me. I hope that you guys liked it, and see you in the next. Goodbye, take care.